Hi everyone, welcome to our session. In this talk, I will present our work, the selective replication in memory-side GPU caches. I'm Xia Zhao from Academy of Military Science, China. GPUs use the shared FLC, where SMs connect to the LC slices through the network on chip. For each LC slice, it caches the data from one memory controller. From the view of SMs, we can access all LC slices and also the full memory space provided by the memory controller. NOC plays an important role in connecting SMs with LC slices. Here, we use the two-stage hierarchical X-bar, which is much more scalable and cost-efficient than full crossbar. In the shared LLC organization, if many SMs want to access the same shared read-only data at the same time, these concurrent memory accesses will cause very serious congestion. This is because the shared data only exists in a single LC slice, and the LLC slice cannot serve these accesses in parallel. For these applications, private LLC can reduce the congestion and provide high data bandwidth by replicating the data across different LLCs. In this way, private LLC organization distributes requests for shared read-only data across LC slices and improves performance. However, the aggressive replication of private LLC can cause very serious cache thrashing if the application has a large input data set. In other words, many memory accesses will miss in the LLC and has to be served by the memory. This limits the system data bandwidth and decreases the performance. Although previously proposed adaptive LLC can choose between shared and private LLC, it's still too coarse-grained. So this is the how adaptive LLC chooses between shared and private LLC. It's very clear it cannot solve the problem. Compared to private LLC, which replicates data across different LC slices, in this paper we propose Selective LLC. Selective LLC selectively replicates shared read-only data across LC slices to improve data bandwidth, while ensuring that the LLC retains sufficient capacity to keep shared data cached. In this way, Selective LLC improves bandwidth while avoiding cache thrashing. Here is the application performance changes with different replication degree. We changed the relative shared dataset size from average 0 to average 4. The relative dataset size increases. Private LLC is good for small shared datasets as it has high LLC bandwidth and limited impact on capacity. Shared LLC is good for large shared datasets because of impact on capacity. Adaptive LLC achieves the best of both worlds. Selective LLC enables more fine-grained control, thereby significantly improving performance across shared dataset sizes. Before I talk the drawbacks of shared and private LLC and give an example to show how our Selective solved this problem. Now I'm going to talk about the mechanism of selective replication LLC. Selective LLC contains two parts, the compile time analysis and runtime support. In the compile time analysis, Selective uses a lightweight compiler path to identify the read-only data structure. In the runtime, Selective uses a bandwidth model to choose the LLC organization with a suitable replication degree to maximize the system data bandwidth. Next, I'm going to show the details of these two parts. We accomplish this by using data flow analysis at the level of the PTX, its intermediate representation to identify all accesses to each data structure and then determine if they are reads or writes. A data structure is read-only within a kernel if its elements are never written within its boundaries. After identifying read-only data structures, the compiler replaces its loads with global data with the special load read-only instruction. To exploit this information at runtime, we add a read-only bit to the metadata of memory requests. Thus, CREP LLC identifies the read-only memory requests by inspecting this metadata bit. This extra bit doesn't add overhead because of a read request only uses a few of the wires in the request, not channel links. CREP LLC can be implemented with minor modifications to the MC router. The replication degree directory RDD predicts if a read-only memory request will hit in LLC with different degrees of replication, as well as the shared and private organization. CREP LLC divides time into epochs. At the end of an epoch, CREP LLC uses an analytical bandwidth model to predict which LLC organization maximizes bandwidth. To predict the LLC misses for all possible replication degrees, we devise a lightweight mechanism we call RDD. The RDD contains a collection of bit vectors which we call cluster ID along with each tag to predict the hit rates of different replication degrees. The counters are used to record the cache access or miss count in different LLC organizations. For the shared LLC, the request is a hit if the tag matches. For the private LLC with a specific replication degree, the access hit when the tag matches and the memory access comes from the same SM cluster. For example, an SM from cluster 3 accesses the cache. Then the tag is updated based on the memory address of the access. The cluster ID of different replication degree is set to 1. In the private LLC, cluster 3 is set to 1. In the private LLC with replication degree of 4, cluster 2 and cluster 3 is set to 1 since they share the same LLC space. Similarly, in the private LLC with replication degree of 2, cluster 3 to cluster 0 is set to 1 since these 4 clusters share the same LLC space. Now, if SM from cluster 2 want to access the same address, it misses in the private LLC with the replication degree of 8. Meanwhile, the access hits in the private LLC with the replication degree of 4 and 2. This is because in these two LLC organizations, cluster 2 and cluster 3 share the same LLC space. After predicting LLC hit rate on the different LLC organizations, CREP uses a bandwidth model to predict the system memory bandwidth of different LLC organizations. The memory bandwidth of the system is the LSP multiplying the bandwidth of LLC. CREP LLC uses an analytical bandwidth model to predict which LLC organization maximizes bandwidth. LSP is used to estimate the LLC access parallelism. Is different in different LLC replication degree. Bandwidth of LLC is the bandwidth of LLC hits plus in the bandwidth of LLC misses. Bandwidth of LLC hit is the hit rate multiplying the LLC bandwidth. The bandwidth of LLC misses depends on the LLC hit rate, LLC bandwidth, and memory bandwidth. For example, if the LLC hit rate is high, which means the memory bandwidth can cover the LLC misses. In this case, LLC bandwidth is the LLC hit rate plus in the LLC miss rate. On the other hand, if the LLC hit rate is low, which means the LLC misses saturate the memory bandwidth. In this case, LLC bandwidth is the LLC hit bandwidth plus in the memory bandwidth. LLC bandwidth and memory bandwidth is the theoretical bandwidth of the system, which depends on the hardware and remains the same for different LLC replication degree. LLC hit rate is affected by the LLC organization. For example, the shared LLC has the highest LLC hit rate, and the private LLC with the maximum replication degree has the lowest LLC hit rate. Next, I'm going to show an example to illustrate how CREP LLC works. In this example, for simplicity, we only show one MC router and assume 4 LC slices per MC router. When many SMs frequently access LC slice 0, CREP predicts LC hit rate with different replication degree and chooses the LC organization which maximizes LC bandwidth. Here, CREP chooses the replication degree of 2. After choosing the LLC organization, SM class 0 and 1 access the LC slice 0 to fetch the data from address X. Meanwhile, SM class 2 and 3 access the LC slice 2 to fetch the data from address X. Initially, this access will cause a miss in the LC slice 2. After fetching the data, the memory accesses from class 2 and class 3 can hit in LC slice 2. Meanwhile, the class 0 and class 1 will access LC slice 0 to get the data from address X. The data replication reduces congestion. Finally, CREP LLC decides to revert to the shared LC organization. All requests for catchline X are now routed to LC slice 0. The replic in LC slice 2 is no longer reachable and will eventually be evicted based on the LC replacement policy. Next are the experimental results. We use GPU sim to do the GPU simulation. We use Descent to do the knock power evaluation, and use GPU watch to evaluate the GPU power. We assume 22 nanometer technology node. We simulate the GPUs with 64 SMs and 48 kilobyte L1 per SM. We simulate 4 megabyte LLC. We use 17 applications. For the replication-sensitive applications, we use underline 0 to underline 5 to represent different input data set and LC size. Here are the performance results. For the replication-sensitive applications, CREP LLC improves the performance by 19.7% on average. Compared to the previous work, Adaptive LLC, which adaptively chooses shared or private LLC, CREP LLC improves the performance by 11.1% on average. CREP LLC is within 2.3% compared to the BSR on average. BSR is obtained by determining the optimum replication degree through offline profiling by evaluating all possible replication degrees. The figure reports the replication degree for the different benchmarks and configurations on the CREP LLC. These results are computed by recording the replication degree for each epoch on the CREP LLC, out of which we then compute a distribution of the replication degree. CREP LLC dynamically selects the replication degree for the given workload and configuration. CREP does full replication for small shared dataset to no or limited replication for large shared datasets. The left figure shows the LLC miss rate, and the right figure shows the data response rate on the different LLC organizations. CREP slightly increases LLC miss rates due to data replication compared to shared LLC across all configurations. By increasing the LLC slice parallelism and avoiding LLC thrashing, CREP LLC achieves the highest effective LLC bandwidth, which explains why it outperforms the other LLC organizations. CREP LLC reduces energy consumption by 5.7% on average compared to the shared cache. The reason is that CREP LLC reduces execution time significantly while only slightly increasing power consumption. We also evaluate CREP LLC on the different configurations and show that CREP LLC is effective across the broad design space. In this paper, we show that shared LLC can cause very serious congestion in GPUs due to the concurrent accesses to the shared read-only data. Private LLC can reduce the congestion, but aggressive replication causes LLC thrashing and decreases the performance. We show that selective replication makes fine-grained trade-offs between bandwidth and IOC capacity. Next, we propose CREP LLC for GPUs. CREP contains a compiler path to identify shared read-only data structures in order to only replicate read-only data. RDD is used in CREP to predict LC mystery under different LC organizations. We also propose a bandwidth model to predict which LC organization maximizes bandwidth. For the replication-sensitive applications, CREP improves the performance by 19.7% on average and reduces the energy consumption by 5.7% on average. This is the end of this presentation. Thanks for listening.